In this video, I'm going to describe how to use onshape to design a motor bracket for an N20 style brushed DC gear motor that could then be 3D printed. So here we see onshape. This is my favorite CAD tool right now. It is free as long as your document can be public, and it works a lot like most other CAD programs. I would highly recommend using a mouse. If you right-click, you can rotate. If you center-click, you can pan. If you use your scrolly wheel, you can zoom. And it's parametric, so on the left here we'll see all of the things that we've added, and the order is important. So what are we going to make? Here is a N20 style motor from Fillet. I've actually ordered motors from AliExpress, which aren't necessarily as high quality as these ones from Fillet. So if you're looking for something that's guaranteed to work, look at Fillet. If you're willing to wait 2 months for shipping, you can order them from AliExpress. An N20 style motor is a brushed DC gear motor, very small motor here, with an open style gear head. This is a little dangerous because stuff can obviously fall into these gears and then chew them all up. I don't think I've actually seen any of that happen before, but it's certainly a worry. It has a 3.5 millimeter output shaft with a flat on it, so you can stick a press fit gear or wheel or whatever you're doing onto that, or you can have a set screw hit the flat from whatever device you're pushing on here. It's meant to be mounted either two ways. One is that you can see there's two tiny, I think they're 1.2 M tapped holes in the front, so you could 3D print or laser cut a plate that sits on this plate and has two through holes in it, and then you could use two tiny screws to screw into this front plate, but then you lose a little bit of the length of your shaft. So the other way to attach to this motor is to make a U-shaped piece of metal or plastic that wraps around the gear head, and then that would of course protect the gear head from stuff falling in it, and then it kind of pinches the motor onto whatever plate that you're mounting it on. Another danger for this motor is that you can see the tabs in the back. This is where you solder wires on to apply a voltage to make the motor spin. Those are very thin, and if you bend them back and forth a few times, they'll shear off flush with the back of this motor, and then you won't be able to grab onto it in any way, and then the motor is basically dead. So the two ways you could damage this motor: letting stuff get stuck in the gears, or stripping the gears, or breaking off these metal contacts. That's happened to me way more times than hurting any gears, so be careful of that. They sell some high power and regular power motors. It just shows different kinds of brushes that they supply. Here's a press fit wheel on the end of that shaft. Some of these motors come with an extended shaft out the back, and you can then press fit on a magnet that has many north and south poles, and then you can get a quadrature encoder on that. Okay, so here's the example of the part that we're going to make. It's a U-shaped piece of plastic that's going to cover the gear head and pinch it against a plate. In this case, the plate is our printed circuit board. And it's going to cover up those gears, and inside, we'll see in a different picture, this U-shaped piece of plastic has some grooves in it that grab onto the brass plates that make up the gear head, and that prevents it from slipping in and out. And then we can use two screws to attach that to whatever our board is. And then Fillet is a great company for motors, and you can see at the end here all of the different styles of motors. N20 is kind of the smallest they make, and then they get bigger and bigger, each using more current and torque. Okay, so in the lab I have provided motors, so you can grab those motors and a cheap pair of digital calipers to grab measurements. If you're not in the lab and you can't grab those, you can grab the measurements off of this N20 motor from Fillet, which might not exactly match the one that we have in the lab, but it's close enough. So the measurements that we are going to care about is L, the distance, the length of the gearbox, the width of those plates, and then the overall dimensions here. I'm not going to make a CAD model of the gearbox. I'm just going to make that U-shaped piece of plastic. So we can also go look at these devices, these brackets. You could just buy these from Fillet. And here you can see there's there's a fillet on the inner edge of the U-shape, and they cut some slits. That's where you can lock in the motor by grabbing one of those plates. And why don't we just grab these dimensions as well? And then, of course, when you design your actual bracket for 3D printing and making of your robot, you might configure it a little differently, but we'll just kind of copy this. Okay, so I'm not particularly good at CAD. I'll show you my method. So what I like to do is make a block. So I'm going to extrude essentially a rectangle, and then I'm going to extrude holes in it until I get the shape that I want. So if we're going to copy these dimensions from Pololu, give us, first we should probably be working in metric. Okay, so when you're in Onshape, you get to see all of your projects. Back into the project I'm making for this class. And I can go to document properties, not document, workspace units, and we'll change to millimeter. And I'm going to make a block of plastic. Let's say it is 15 by 11.5 millimeters on the front plane. So I'm going to click that plane, and I'm going to look at it from the front, and I'm going to say, make a sketch. I'll grab the center point rectangle, the origin, my width again. My width is 15 and my height is 11.5. Okay, so that's a block. That's the front face. And then I can take that sketch and extrude it 17.3 millimeters deep. Now I can cut a hole in that front face by drawing a sketch on that face. This time I'll use the corner rectangle tool, and it will snap to certain parts, so I will snap it there. And then I'll grab the dimensioning tool to essentially give this a wall thickness. I don't know, I'll say it's a 1 millimeter wall thickness. So now I have that sketch on his face, so I can say, I'll select that sketch, I will grab the extrude tool, I will say remove instead of add, and I will go through all. Okay, so now I've got my U-shaped piece of plastic. It should have some, I don't know what to call these, fins on the sides, so that I have holes to screw into. So I'll grab that front face. I'll sketch more rectangles on it. Here's a neat thing you can do in Onshape. I'll click one corner, and then I'll just mouse over another point and snap to that point. And I'm not really using great dimension here. Oh, that might be good. Corner. and then I will extrude those. I'll have to go the other direction. I only want them to go 3 millimeters deep. Adding, and because they're the same color here, we can see that they're going to merge as one part. Okay, these don't look particularly like the right scale, and I should be using my calipers or going off of these dimensions. Let me just do it by eye for now. Have this go out 5 millimeters. 5 by 5 millimeters. Okay. Then on this surface, I'll put some holes. And I should be basing these dimensions off the size of my screws, but I'm just going to eyeball it. Okay, so the motor would slip into this hole, and then I would have screws go through these holes into the holes of my printed circuit board, and then nuts to hold that on. The last thing I want to do is make sure that the motor can't slip in and out of here. I'm going to select these two edges, and I'll give them a chamfer. You could also use a fillet. And the only thing you want to be sure here is that if you fill it too much, you might hit the gears that are in that box. So you'd have to look at those gears. In every motor, gear ratio might have different number of gears, and the gears might stick out closer to the side, so you'd be careful about that. And so on this bottom face, I'm going to sketch the slits. Actually, it doesn't want to snap, so I'm going to this face sketch. So we'll pretend that this motor has 3 plates located at these positions, and of course these should be actually measured. And I'm just going to guess that each of those plates is 1 millimeter thick. And the first 2 plates are 8 millimeters apart. Oh, some kind of auto. I must have hit a midpoint or something there. Okay, we're just going to leave those. Remove, and we're going to go next. Oh, okay, so our motor, which has 3 brass plates in it, would kind of slip in there, and that would prevent the motor from being able to move in and out of here. And then maybe the last step is to pretty it up a little. We could grab the fillet tool, just knock off some of these square edges. A reason for this might be that we're trying to reduce stress concentrators. Another might be just to reduce printing time by getting rid of some volume, or just make it look pretty. These ones, for instance, probably a bad idea because it's going to interfere with the screw or the nut, but fine. Okay, but you can see that really jazzes up the design by adding some fillets. Okay, so let's assume that I took all those measurements and I was happy with this design. To 3D print it, I would export an STL file. So I'd right-click on part and say export as an STL, millimeters fine resolution. And then to see how this would print, I'd switch over to my slicing software. So I like to use Prusa 3D printers, and there's a couple Prusas in the lab. So you can download the Prusa slicer, and then in it you can open your STL file. And in the slicer, you get to choose which way, what's the orientation of this print. Now this would be not the best orientation, the default, because this top shelf has no support under it. So I could either turn on the support option, but it might take longer to print, or I could try to orient the print a little bit differently so that it doesn't need support. So I can click on the device and I can rotate by 90 degrees. And maybe that's a better print orientation because now we don't need as much support. The only downside would be the slits that I kind of wanted a very specific distance apart. They don't have supports. So you could print in this orientation and see if it fits, or you could print in, maybe I should go, might be the best. Let's go another 90 degrees. Print upside down, and then these shelves might not be supported, but they're not super important that they're exactly the right distance. So that might be okay. Or I could turn the supports on now and there'd be less support than if it was 80 degrees off from there. But in this configuration, you get the best slits because they print straight up. So you can play around with that. And you can play around with the settings. Usually the Prusas are fine at just doing their default speed, so I wouldn't go with ultra detail or 0.15. I would go with the 0.2 millimeters, maybe for quality or speed. At this volume of stuff, it doesn't really matter. And if you say slice now, you can move the slider around, and you can see what each layer is doing as a 1 millimeter thickness wall here. Basically, this part prints solid with no infill. And maybe I should turn on sports just to see what happens. Slice. Now you can see that the support material under there, it's that little zigzag pattern in green, and that would just tear right off after doing the print. And let's see, what else does this tell us? How long it's going to take to print? 16 minutes, very reasonable. Of course, it's not going to be very strong, so if you wanted to make it thicker, it would take more time to print. Exporting this G-code would then go on a thumb drive or a micro SD card, depending on which printer you're using. But we're not going to do that in class. So all you need to do for the homework assignment is provide to me a screenshot of your design, and you might as well generate the STL file and open it and upload that. Okay, so this was using onshape to develop a simple motor bracket and output the STL file that you could then 3D print from.